Good afternoon, everyone. Thank you for coming and watching the iGEM Cybersecurity Seminar. My name is Daniel Conte-Leon, and I am a faculty member here at the Center for Secure and Dependable Systems at the College of Engineering. Today, I would like to talk about motivation and principles for developing safe and secure software systems. So the plan is, first I'm going to talk about what is safety and what is security and what the relationship between the two of them is. Then what is the problem that we have today? What is the overall motivation for trying to tackle that problem? And what approach I believe we should pursue in order to try to address the problem. Then I plan to introduce a couple of two different approaches to design, useful design principles. One of them is with respect to security, and the other one is with respect to safety, but you'll see that there is a strong relationship between them as well. Then I will show you two example problems, and although the problems are somehow, the explanation is somehow technical, I'll try to make it clear enough for the people in here that are not computer science people like my background. And then I will go to summary and questions. But if you have any questions during the presentation, please feel free to ask for clarification. Within the introduction, I want to introduce first what critical systems are, and then what the relationship between safety and security is, and definitions of safety and security. So first we have what is defined as a safety critical system. A safety critical system is a system in which great losses or damage to people on the environment may happen if the system fails. Examples of these systems are, for example, an aircraft, air traffic control, any medical equipment devices, power plants and the power grid, and transportation control systems or other systems that are known as SCADA or ICS and industrial control systems. In general, in the literature, we say that when a fault that is in a system gets exercised, then we have an error, and then that error may lead to what we call a hazard, and then the hazard may develop into an accident, and then from the accident you may have loss of life or loss of property or loss of the system. With respect to security critical, you see that there are many similarities, except the language that we use in academia and industry is a little different. Also, you could have great losses, but instead in this time the losses will be either to data or privacy, or there could be loss of service, and associated with those, there could be a great financial loss as well. Examples of these are, for example, sensitive information systems, for example, your banking, or credit card processing databases and systems, and also the power grid. The power grid, because today is being interconnected and even connected to the internet, then it makes the power grid being currently a safety critical system because of the safety implications of errors, and also a security critical system because of the security implications of its interconnectedness. In the security critical nomenclature, we say that a fault could lead to a vulnerability in the system, and then if the vulnerability is exercised, then it's usually exercised for what we call an exploit. And then when the exploit gets executed in the system, then you get an incident, and then that incident could result in loss, and that could be great loss, either financial or on data. So you can see that in both these cases, what is needed is that both of these systems are developed with high assurance that they are correct, and that means that we need to ensure that the functionality of the system is implemented at the same time that the security and safety properties of the system are implemented. And this is hard to do, and I'm going to show you some examples. I wanted to talk a little bit further about the relationship between safety and security. And in reality, safety and security are two sides of the same coin. And the reason we're trying to stress this is because there are many techniques that have been developed in the security community that could be used for safety and vice versa. Many techniques that have been developed for security that could be used for safety. The main difference that you will observe will be that when you talk about safety, you're saying that the safety could be defined as the absence of damage to the environment by the system or to the system itself. And in security, you will say that security could be defined as the absence of damage to the system or any of its components. And you can see that the difference between those two really resides on where do you put the boundary of your system. If you make your system bigger, your system view bigger, then you're putting more components within your own system. So then you're making more of a security view. But if you make your system smaller, then what is outside your system is what could be damaged if your system misbehaves or it has an error. So the relationship there is very strong, and also the boundaries of the system are not fixed and they're not static. They change depending on what view of the system you're having. For example, whether you're making an analysis, do you consider the air traffic controllers within your air traffic control system? Do you consider them an essential part of it? Or do you consider them to be outside of the system? And that really depends on what the purpose of the analysis you're making is. Just to show you a little bit more about how strong the relationship is in here and how much we could reuse carefully techniques from one area of research and practice to the other. If you translate the word security in the first one is in Spanish, the second one is in French, and the third one is in Italian, then those are the words you get. I'm not going to pronounce them because I don't want to mispronounce them. Now, if you translate safety into Spanish, French, and Italian, that's what you get. Do you see the similarity? Yeah, in many languages, security and safety are actually the same concept. Or at least there is one concept that englobes both of the concepts that in English we call security and safety. So what's the overall problem and what is the motivation? I mean, you see that is almost obvious, but I still like to state it. And then what approach I believe we should pursue. So the problem is that all of these properties, what we call the ilities, like security, safety, and all of the dependability properties, are actually what we call emergent behavior. They're usually not something you can observe by looking, for example, at one part of your system and say, oh, this part is secure, therefore I combine it with this other part that is secure, and this part is safe, and I combine it with this other part of the system that is also safe, and at the end I get a safe system. That's not the way it is, sadly, because that will really facilitate the way we develop systems. And I'm going to show you, when I show you the examples, how this is not the case. So that means that you really can't observe these properties until you put all the system together. And by together, I mean holistically. You can't look at the air traffic control system without also looking at the air traffic controllers as people. You can't look at these components in isolation because you won't see these errors. To make things worse, we are making our system more and more complex. And not only that, now we are interconnecting them to each other. So meaning we are making them even bigger. There's also a wide range of faults of causes and errors. And we're going to see two examples of them in a minute. So the motivation is that these computer-based or software-based systems, we are using them for more and more and more applications. And that's because they're very flexible And we can do a lot of things in software that you can't do otherwise, or you can do things in software cheaper than you can do without having software. And these systems are becoming part of our life. They're becoming essential to life and well-being and our well-being. And even if not everything you do every day is on a computer, you're still affected by these computer systems. For example, if there is a system that controls an oil pipeline and the system fails and there is an enormous spill of oil, you may be affected by it. And even if you're not close to it, you will still be indirectly affected. So either directly or indirectly, we are affected more than what we would like to by these accidents. So the motivation is we need to make sure that when we develop these systems, we do them in a safe and secure way. So the approach is that we need to do this holistically. We can't try to attack all these problems separately and then try to glue everything together and hope that everything works. So we need good guiding design principles, although these are just rules, they are not silver bullets, because the fact is we don't have a silver bullet to develop these systems in a safe and secure manner. We need robust development methods. We need to be able to build strong assurance cases for each of the systems, and each of the assurance statements that we make, we need to be able to justify them. We need a good modeling and analysis tools depending on the system, the subsystem, and the view that you currently have of the system. And holistically, when I say holistically, I'm talking about it in both meanings. I'm talking about it, we need a comprehensive set of approaches, and we also need to look at the systems in a holistic way, like the example I gave earlier about the air traffic controllers as people being analyzed and included within the complete air traffic control system, because the air traffic controllers are also part of the system. You can't separate if you want to look at the emergent properties, or at least be able to infer something about the emergent properties. It's been shown that you also need good management, because no project gets well developed if there is no good management behind it that has the commitment to ensure that these properties are being met. And then we also need education and training. So you need to make sure that you educate the workforce of the future and that you train your current workforce on how to develop safe and secure systems. And lastly, we also need research and improvement. So we need to put all of the above approach into a cycle of improvement, because what works today may not work tomorrow, because the systems and the assumptions may change. Any questions so far? All right, so let's look at the useful design principles. And first, I wanted to show and give an explanation of the secure software design principles and then the safe software design principles. So the first one is something that was developed by Salcedo and Schroeder in 1973 and 1974. There are 2 days, because the paper was actually published twice. It was such a successful paper that it got published, I believe the second time in the ACM Communications. So this is about 4 years old, and these principles were developed originally thinking about operating system, secure design of operating systems, but all of these design principles still apply today to most of the systems we develop. And the first one is economy of mechanism. An economy of mechanism is also called, sometimes called Occam's razor. And economy of mechanism means that if there are two options that are equally possible and they're the same with respect to your system, you should choose the one that is the simplest. The second one is fail-safe defaults. And in fail-safe defaults means that if your system is going to fail, you should have it fail by default on the option that is going to be the safest or the most secure. For example, if your car ABS system, which is a computer-based system, is going to fail, would you rather have the car lose the braking ability, or would you rather have it having brakes without the ABS? The answer is obvious, right? Because I chose a case that is obvious. But many times the answer is not so obvious. Complete mediation. Complete mediation means that when you're checking for access permissions, you need to make sure that you do that all the time for every access that is requested and for every user or object that requests access to the system. And I'm going to give you an example later on of Apple vulnerability, what is called the go-to-fail vulnerability, in which they actually did fail to make sure that all the access was executed and verified for all the instances of all the possible cases that were requiring access to that object. Open design, it means that you should try to make your designs open for the purpose of many people looking at them and piggybacking on the ability of many different eyes looking at your system in order to tell you whether your system may have a problem or not. Of course, commercially, this is hard to implement, and you'll see that for the case of all these security design principles and also the safety design principles that I'm going to talk in a minute, implementing all these principles is not easy because they're conflicted. When you try to maximize one principle, then you're minimizing the other. It's a hard task. It's not a silver bullet. There are no silver bullets. For example, one case of open design will be cryptography. It's very well known in cryptography today that you don't create a cryptographic algorithm that is secret and pretend or expect that the secrecy of the algorithm is going to protect you. Because if you're going to distribute the algorithm to pretty much all your people within your organization, then you're probably going to lose the secrecy pretty quickly. So we know that in cryptography, what we do today is we make open designs, so the cryptographic algorithm is open and is separated from the key that is used to unencrypt. So for example, SSL and TLS, which is the protocol that is used when you communicate to a website, when you want to communicate to your bank website securely, is a very open algorithm. It actually uses many algorithms, but it's a very open architecture. And it uses keys that are generated whenever you connect to your website. So what changes is the key, but the algorithm stays the same. Least privilege means that you should always give the permissions that are necessary for that object to carry its task or for that person to conduct his job, and not more. For example, in order to perform my job duties here at the university, I may need access to some doors. There's no reason why I should get access to all the doors on campus because I don't need that in order to perform my job. I should get access only to the doors that I need in order to perform my jobs and no other. The same could be applicable to files. For example, what files could you access in your company? Well, you should only have access to the files that you need in order to perform your job. Least common mechanism, and here is where you see where things, a clear example of how these principles are conflicted with each other. And that's why it's so hard to develop systems that comply with all these systems at the same time. Least common mechanism means that you should minimize the amount of entities that are common to your whole system. For example, the Apple case that I'm going to describe in a minute is a case in which they use a library, this particular an SSL TLS library, and they use this library is the same library that is used across all Apple products. So your iPhone or your iPad or your Mac or your Apple TV, all of them use exactly the same library. And you could say that that approach will violate the least common mechanism approach, because the least common mechanism approach says that you should minimize the amount of things that are common to all the mechanisms. Now, of course, there is a trade-off. There is an advantage of doing this, right? If you create only one SSL library, then you can reuse it across your other systems, and you don't have to develop one or two or three or more than one. And also, for example, when you have to make a fix, then you only have to make it in that particular library, and then you can push the fix to the other. So there are trade-offs to doing one approach over the other. So there is not one single goal answer. And then psychological acceptability, and I'm also going to add into here, I will say psychological and social acceptability. For example, an example of this will be if your bank website or a website that you need to connect every day in order to perform your job requires you that you enter 10 different passwords, then that's probably not going to be psychologically, socially acceptable by most of the employees. So what's happened is they're going to look for workarounds. And if you're looking for workarounds, they're going to defeat the purpose of your technique. So you need to be sure that when you choose these techniques in order to make your system more secure or more safe, that your approaches are acceptable socially and psychologically to the users of that system. For example, in one of the errors that I studied and reported, this was an error in an airport in which there is related to air traffic control, in which there is a system that would warn the air traffic controllers in the tower that an aircraft is approaching the airport and is actually approaching the airport given the airport characteristics too low given the airport characteristics. For example, there are mountains around it, or the airport is at a certain elevation compared to other airports. And that system had audible signals. They had speakers within the air traffic control tower. And in many years ago, it happened that this system was in some of the airports, or at least in one of them, this system was giving so many spurious warnings that the people ended up blocking the speakers with tape because it was impeding them from carrying their other jobs correctly. So again, you can't see these things until you look at these systems holistically. When they design the system, we'll create an audible warning, but if the audible warning is really a nuisance, because most of the time the warnings are not adequate, or they are not a danger, then things like that may happen. So you have to look at these things holistically. With respect to the safe software design principles, these are newer. These were developed by Hawkins, Havley, and Kelly last year, and they call them the 4+1 principles of software safety. And these ones were developed with a different goal. These ones were developed by looking at most of the current safe system development standards, by looking at what the standards require and putting that in a high level picture view. What do all standards require that you do in order to develop a safe system? You'll see that these ones are also applicable to security, same way that the secure design principles will be applicable to the design of safe systems. Now you'll also see that the approach is also different. These ones are more process-oriented, whether the Salzer and Schroeder principles are more characteristic or property-based. These ones are definitely process-based. So the first one is safety, and I added system requirements. You need to be sure that you adequately gather your requirements, and you adequately gather which are your safety requirements. You could also say you adequately gather your security requirements. What are your security requirements? And then be sure that you establish those adequately, correctly, and completely. For example, you want to make sure that, for example, let's talk about medical devices. And there's one case in which there were insulin pumps that when the user pressed the button, every time the user pressed the button, then it will change the dosage. And then it happened that sometimes the button will believe that it was pressed more than once. Will that be a safety issue? And yes, of course, it will be a safety issue, and it was a safety issue. So you need to be sure that you analyze the system from that point of view. What can you do in order to prevent that? Because the functional requirement is exactly, I would like to change the dosage by a certain amount, let's say 10 milligrams per liter. I don't know, I'm not a doctor, so I don't know exactly how the numbers fit in there, but the functional requirements is you would like that the user can change the dosage by pressing a button. But the safety requirement is, well, is there a danger that the system will misunderstand how many times the user pressed the button? So there's a separation between the functional requirements and the security and the safety requirements. The second one is the composition and traceability, meaning when you come up with all the requirements, the functional requirements and the security and the safety requirements, and you assume that you have all of them, they're complete and correct, then you need to ensure that when you decompose them into smaller requirements, so you can actually build a system that implements those requirements, that you decompose all of them correctly and that you ensure that there is traceability between the things that you have decomposed and the overall requirements of your system. And this applies not only to the point of the first division that you make between requirements and the first level of the requirements, but it also applies throughout the development process and all the work products of your system. For example, you need to make sure that there is traceability between the functions or the chips and pieces of hardware that are in your system, which ones implement what portions of the overall requirements. And you need to make sure that that information is available so you can analyze it and make it available to the users and developers. The third one is requirement satisfaction. And you see that there is a relationship between these ones, as you need to ensure that all those top level requirements, when they're complete and well written, then you need to make sure that you are actually implementing them. For example, the Apple Go to Fail example case that I'm going to talk about in the next point of the presentation gives you an example of what happens when you don't ensure that you have implemented the requirements completely. And this has to do with implementation. You need to make sure that, although assuming your requirements are correct and complete, you also need to make sure that the system portions, functions, and hardware that you created and architected are actually completely implementing all the requirements that you said you'll have. And this applies not only to functional requirements, which is usually where we put the stress, but it also applies to the safety and the security requirements. The fourth one is what is called hazard identification and mitigation. And this is a process that you need to conduct in order to develop safe systems and also secure systems. If you substitute the word hazard by vulnerability, then you could apply the same thing to secure systems. You could say vulnerability identification and mitigation, which is one of the processes that we use in order to develop secure systems. So, for example, when you are developing a system, you need to make sure you try to look at all the possible hazards. And again, this is really hard to do because it requires you thinking about all those possible things that could go wrong, even when you never heard about it. For example, there was an accident. Sadly, in this accident, people did die. There were 2 people died in this accident. This was a Warsaw accident. This is an aircraft-related accident in which, for this plane, one of the models of Airbus, the engineers decided that there are 3 ways that you can ensure that a plane decelerates quickly as soon as it lands. And those 3 ways are the brakes on the wheels, what's it called? The spoilers, the spoilers that are the things that lift from the wings So, they reduce the lift and then reduce the airspeed with respect to the plane. And also what is called the thrust reversers. So those three things, from those three things, the brakes, if you are still flying and you're not on the runway, they will have no effect, except if you're pushing the brakes at the instant you land, that may be a problem. But the thrust reversers and the spoilers is something you don't want to do when you're in the air. That will be a catastrophe, because then you will lose the lift. So there is a system in place that prevents that the thrust reversers and the spoilers will get activated when you're still in the air. So it makes sense that there is an overall safety requirement. I would say thrust reversers and spoilers should not be activated while the aircraft is still flying. That makes sense, right, for everyone. Is that correct? Now, when you look at how you can implement this, then that's where you need to make sure that you look at all the possibilities from the point of view of doing hazard analysis. Excuse me. The way the architects in this particular instance, and this was corrected, decided to implement this overall requirement was, well, why don't we make sure that there is pressure? In this case was 12 tons of pressure. We're talking about aircraft that are weight more than 100 tons. 12 tons of pressure in each of the main landing gears, so the ones in the center of the plane. So 12 tons of pressure in each of the landing gear. Then if we sense that, then we can be almost certain that we will be on the ground. And then that's the first thing that you do to sense the environment, whether you're on the ground or not. And the other thing is, well, let's make sure that we are going at 72 knots, the wheels are spinning faster than 72 knots, the equivalent speed to 72 knots, meaning you're on the ground and you're running on the runway. So with those two things together, if one or the other are true, then you can enable the spoilers and the thrust reversers. And actually, in this particular case, the way things were implemented is if both of the main landing gear had pressure on them, then you will activate the thrust reversers. And then if one or the other were true of either the landing gear pressure or the speed on the wheels were true, then you will activate the spoilers. So that's the implementation that the engineers decided to architect in order to implement this requirement. And we all agree that this requirement is a good requirement to have. Now, this system did have no what is called a pilot override. It was completely automatic. The pilot could not shut it off. What happened in this particular instance, and again, we go back to we can't look at these things and discover them if we don't look at these systems holistically. But back to doing hazard analysis, what happened in this particular instance is that when the aircraft was landing, it was bad weather, it was raining a lot, and there was a lot of wind. So do you think it would be possible? Let's say that you were an aircraft designer. You think when you're designing this system, you think it would be possible that an aircraft in a particular instance will be having only one of their landing gear on the ground? Do you think it's possible? No? Well, it is possible. In this particular instance, it happened. There was a lot of wind and the aircraft was lifted from one of the sides. So there was not enough pressure, although the wheels may have been on the ground because the air was lifting the plane so much, there was not enough pressure for the system to say, oh, we are on the ground. At least not on one of the wheels, not on one of the landing gears. It was, of course, on the ground on the other landing gear, but only on one of them at a time. Do you think also it's possible that in addition that the landing gear that was on the ground was actually not spinning? The wheels were not spinning at more than the equivalent of speed of 72 knots. Pretty weird sequence of events, right? Now, when this happened, yes, it did happen. It was raining a lot, the runway was very wet, and the airplane was actually skidding on the runway and not rotating or rolling. So the wheels were not rotating. So when that happened, then what happened, and then the pilot could not override this system. The computer said, I'm sorry, we are not on the ground. I can't enable the spoilers and the thrust reversers. And the pilot knew that it was kidding and didn't have a lot of time or runway to brake, because at the end of the runway, there was a big mound in this particular airport. This was in Warsaw. The pilot wanted to make sure he enabled this before he hit the end of the runway. But he couldn't override the system. The computer was saying, sorry, we're not on the ground. So that shows you that you need to be very careful when you do hazard analysis, and you need to make sure that you try to look for all the possible things that could go wrong. And that is really hard. It's hard for several things. First, you need to think about all the things that could go wrong when you've never seen them. And second, sometimes you have limited time to develop these systems, and you also have trade-offs. How much time do I have to analyze this? How much money do I have to spend on this? And I want to make clear, the aircraft manufacturing companies are among the best manufacturing companies in the world, and the aircraft and airport transportation systems are the safest system in the world. Statistically, you will be safer flying than you'll be when you're driving your car. So these are companies that do really good things, but these problems are still really hard. And the last one, and that's the reason they call it a 4+1, is what is called confidence and assurance. And this one pretty much is the all of the above. When you do all of the above, you need to make sure that for each of those analyses that you made, for example, the hazard analysis or testing, if we're talking about security, if we're applying these principles to security, you need to be sure that you have a strong assurance case. If you're going to say that these requirements were implemented by this system, for example, complete mediation, in any case that somebody requests access to the verification of this system, for example, a security certificate from a website, you need to be sure that in all the cases, the security certificate and the keys associated to it are verified to make sure that everything is correct. That's not what happened in the case of Apple. Any questions, Far? So let's look at two example problems. One of them is the Apple Go to Fail, which is a pretty recent problem, and the other one is a vulnerability in an Oracle database. So the Apple Go to Fail is a vulnerability that was introduced in what is called the SSL TLS library, which is the library that is used when you connect to a website securely. So you want to connect to your bank, you're using this library if you're using an Apple system. The exceptions are if you're using Chrome, for example, or Firefox, then you're not using this library because Chrome and Firefox embed their own SSL libraries in the software. But if you're using an Apple product, before they fix this vulnerability, which they have, of course, you were running this library that had this vulnerability. So it included all the iOS platforms, which is the iPad and the iPhone, and the iPad, the Apple TV, and also the OS X software, which is the one that comes with Macs. They issue a security update for iOS on February 21st. This vulnerability was first reported. It's not clear, but some people believe at the end of January. And then the update for OS X was pushed on February 25th. It was actually the first update of 2014. So let's see if I can explain this in a way that the people that are here that are not computer scientists can understand, and I believe I can. This is one of the functions, particularly the function that was vulnerable. Now, SSL and TLS is a very complex protocol. It has many different options and ways of ensuring that you do enable encryption. So not all possible paths of you connecting to a website were vulnerable. The vulnerability here was what is called a vulnerability to a man-in-the-middle attack, which means, for example, if you're in a coffee shop and you are using a laptop to connect to your bank, and you were following this part of the software, which is what is called the one that implements what is called forward secrecy, which is making sure that everything you do cannot be read even up to the future, because the server, what the server commits to do is create a key to encrypt all the traffic and then throw away the key. Now, yes, it could be that the server doesn't throw away the key, but if the server is not malicious, meaning you trust your bank, and then you're connecting from a coffee shop, somebody else that is in the same coffee shop could capture all the wireless traffic, pretend to be the bank, and sit in the middle of the traffic between you and your bank, and then fool you to believe that you're your bank, and then you will believe that you're doing all the transactions securely over the internet, and the attacker that is sitting in the middle is capturing all the traffic. And for example, you say, send $100 to this account, and the attacker could say, okay, I did that, but in reality, send $1,000 to a different account. The way you prevent these attacks is by ensuring that the bank is who you believe it is, meaning the bank issues you a certificate, and then the software is supposed to verify the certificate. In this particular case, it didn't. And the reason for that is because when you look at this function, which is the one that does one of the stages of the verification of the certificate, in this particular case, the verification of the keys, goes through several stages, and those stages are each of these if statements. And these dots in here means that there are more. This function is much longer. There are many of those if stages. And in here, when I say ERR, which is error, equals, not equals 0, if the error is equal 0, it means there was no error. And I did successfully verify whatever was being called in here, in where these 3 dots are. So let's say that's the first part of the verification. If I go through the first part of the verification and then I get no error, then I jump over and I go and verify the second part. And then I say the same thing. Okay, let's verify the second part of the certificate or the second part of the key. Or actually, you need to do both. If there is no error, then keep going. So if you see that there is an error, for example, let's say one of the portions of the validation failed, then you jump to what is called go to fail. And go to fail is here, this is fail, so meaning if something fails in this series of cascaded checks, then you go here and then you return the error. And because the error is not 0, then your overall function, the SSL verify sign server key exchange, is going to return a number that is not 0, meaning the verification failed. Now, the vulnerability resides on this error here, which is actually a programming error, which is the repetition of this go to fail statement. And what happens here is that if you look at the way C works, is when this if statement, when you execute this if statement, if the statement is true, you're only going to execute the first line immediately under the if statement. The second line, so this second go to fail, is really outside of the if statement. If you're looking at the tabs and you wanted to put this in a way that makes sense with respect to the tabs, this go to fail really will be at the level of the if, meaning the go to fail is being executed no matter what, whether the verification, this verification happened or not. It's actually being executed no matter what, whether the other verifications were successful or not. It's actually being executed all the time, because these if statements are independent from each other. And the only thing that is putting them together is this call at the end, which is SSL raw verify. So the vulnerability resides not just in the fact that there is a repeated go to fail that always gets executed, but it also resides on the fact that when you execute a go to fail, you're jumping over from go to fail onto fail, and then you return the error, and then what happens is that you did not successfully verify. So how can you prevent this vulnerability? Well, there are several ways. One of them is you use coding style to add brackets. If you add curly brackets, then you will prevent that problem because now the second going to fail will be inside the if statement. The other way will be used to use compiler warnings. For example, use the unreachable code compiler warning in CLang or the everything compiler warning in CLang. And this is when you compile, then this vulnerability will get caught. Now, when you compile with -w all, which is the standard way of compiling in GCC and CLang, then you don't get any warning about this. There are also other tools, for example, that are called source code analyzers, and these are commercial source code analyzers, for example, Coverity, HP, Fortify, and DoubleCheck, and all of these tools will discover these problems. And also, if you did code coverage testing, so you did testing to make sure that all the possible paths in the code were executed. So the answer is, can we detect these type of errors? And the answer is yes, this is currently state of the practice. So the fact that Apple did not do this and we had that vulnerability, it means that it verifies the strength of our previous holistic approach, saying it's not enough just to have tools. There is also organizational issues that you need to look at. So what principles were violated here? Well, of course, complete mediation because they did not verify the certificate in all the possible cases. Traceability because their code did not really implement all the security requirements. So the second vulnerability I would like to show you is the Oracle DBMS. Oracle DBMS is one of the most widespread used database service in the world. It's most likely that some of your private information, including your social security number, it is housed in an Oracle DBMS database. The vulnerability here was in the authentication process. The authentication process, the way it works is a username tries to connect to the database and makes a request. The database responds back with acknowledgement, say, okay, I know who you are. These are the parameters of your connection. Then the client responds back with the username, its password obfuscated, and then a set of configuration options. And then the server says, okay, you're all good, you're connected, now you can issue transactions onto the database. In the attribute value pairs, which is what goes into the third step, there is an option to allow you to issue SQL statements. And the purpose of these SQL statements is really to allow you to, for example, change things like your language. What language do you want to connect to the database using the database? What happened here is that the DBMS failed to properly verify the authorization. It did verify the authorization after you were logged on, if you had permissions to do something or not, but it did not verify that you had authorization to run that particular SQL statement that was included as part of the logon process. And not only that, it ran that SQL statement, which is what is called sys or system privileges. Meaning, if you're a normal user, you could run an SQL statement at the system level to create another user and then log on with another user with all the privileges you would want to have. That's what this is called a privilege escalation. So what principles were violated here? Well, complete mediation, of course, because the database failed to ensure that in all cases the permissions were verified. And then requirement satisfaction. The security requirement that every user should log on and be able to do what is allowed to do was not implemented adequately and correctly by the system. So the question is, can we detect these type of errors? We talked about the earlier error saying, well, really, currently, given the state of the practice and the state of the tools we have, that was an error that currently we can detect. But not all errors are that simple. Actually, most of them are not. Can we detect an error like this one? Well, I believe we can. And we are currently researching at the center some techniques and approaches in order to try to discover these errors. I don't have the time to show you those today. So stay tuned. That in other seminars we'll talk about it. So summary and questions. The context is that safe and secure computer systems are essential to today's society. Safety hazards and security vulnerabilities could lead to great losses, either of life or data or financial losses. We require a holistic approach. There is no silver bullet. We need to use an all of the above approach. We need good principles. We need good assurance techniques so we can build a good assurance case. We need good management. We need training and education, and we need adequate processes. I showed you 2 sets of guiding principles. Those that were developed for secure systems and those that were developed for safe systems, though you could use them exchangeably. And then I also show you 2 examples of errors. So stay tuned that in future IGEM seminars, we'll try to show you what techniques you can use in order to try to discover these vulnerabilities so you prevent them to becoming errors or that will lead to great losses. So thank you. Any questions? Alrighty, thank you very much and see you next time.